When you slam on the brakes on a busy highway, your physical intuition tells you exactly what is happening. You feel the forward momentum and the friction, the heavy, tangible reality of the physical world. But human intuition is often an unreliable guide. We operate on the assumption that the total distance our car traveled is identical to its final displacement. We look at the asphalt beneath the tires and see a dense, unbroken solid. Physicists, however, have long suspected that this solidity is an illusion of scale, that the materials we touch are composed of structures that are far less substantial than they appear. To test these suspicions, scientists had to look past static objects. They began tracking the precise trajectories of things in motion. Analyzing the exact geometry of a moving path provides the data necessary to bypass our flawed senses. This mathematical approach governs everything from a braking car to the behavior of invisible, microscopic particles. Consider a car's speedometer. This dial measures a scalar quantity, magnitude. It provides a raw number, but it offers no information about which way you are heading. Calculating a final position requires a vector. A vector combines magnitude with a specific directional component. You aren't simply moving at 60 kilometers per hour, you are moving at 60 kilometers per hour due north. In physics, this distinction separates the scalar concept of distance from the vector concept of displacement. A car navigating a winding road covers 60 kilometers of actual distance. Its displacement is the straight line vector connecting the start and end coordinates, perhaps only 25 kilometers. Average speed is calculated by dividing that 60-kilometer distance by the trip's elapsed time. This relationship between direction and measurement becomes even more apparent when motion is no longer linear. Look at runners entering the curve of a track. Even if their speed remains constant, their velocity is continuously changing. Because velocity is a vector, it is tied to direction. As the curve forces runners to turn, their directional vector shifts every microsecond, altering their velocity. By focusing on these changing vectors, rather than just raw speed, we can accurately calculate how objects move through three-dimensional space. These same tracking principles eventually dismantled the traditional view of the atom. In the early 1900s, scientists hypothesized that atoms were dense spheres of mixed positive and negative charges, the Plum pudding model. In 1909, Ernest Rutherford tested the integrity of this solid structure by analyzing particle trajectories. His team fired heavy, positively charged alpha particles at high speeds toward an extremely thin sheet of gold foil. If the Plum pudding model were correct, the dense mass of gold atoms would either stop the particles or cause them to bounce back immediately. The data showed the opposite. The vast majority of alpha particles flew through the foil as if nothing were there, maintaining their original vectors. However, a small number of particles were deflected at extreme angles, some ricocheting directly back toward the source. These specific deflection vectors proved that the atom is over 99% empty space. The gold foil only seemed solid because a tiny, dense nucleus at the center contained nearly all of the atom's mass and positive charge. Rutherford continued to track these particle ejections, and by 1919 he identified the presence of distinct positively charged protons within that nucleus. In 1932, James Chadwick conducted further experiments with particle collisions and discovered a different type of subatomic particle. These particles had a mass similar to protons but carried no electrical charge. They were named neutrons, providing the final component of the modern nuclear model. This discovery clarified the fundamental composition of matter and earned Chadwick the Nobel Prize. Mapping the trajectories of microscopic collisions allowed physicists to reconstruct the interior of an object they could never actually see. The exact same laws of kinematics govern both the macro and the micro. A car decelerating on a highway and a subatomic particle deflecting in a lab are both subjects of the same vector mathematics. This data is used daily to establish highway safety limits and to develop effective shielding for industrial radiation. By mastering the mathematics of distance, displacement, and motion, we moved beyond simple observation. We charted the structural logic of the universe itself.